two types of nuclear equations up on the board right now, neither one of which represent radioactivity. What's the first one called? It's not radioactivity, it's nuclear fusion, right? Nuclear fusion, because it involves two lighter nuclei forming or fusing together to form one heavy nucleus. Now, we've also got a neutron produced there, and we've also got some energy produced there, but we're not going to worry about that in determining what type of reaction it is. When two light come together to form one heavy, then we've got a fusion reaction. What's the second one called? This one would be nuclear fission, right? This one's nuclear fission because in this case we have one heavy nucleus splitting apart into two lighter nuclei. Now we've also got some neutrons, in fact neutrons on both sides of the equation this time, and some energy produced as well. And that stuff's all important, but it's not important in determining what kind of reaction we have. When two light form heavy, independent of the other stuff, it's fusion. When one heavy forms two light, independent of the other stuff involved there, then we've got nuclear fission. Now, nuclear fission occurs when we bombard uranium-235 or some other fissionable material. Uranium-235 is not the only one. It is some other fissionable material with a neutron, causing it to become unstable. And it quickly decays into a couple other elements plus some extra neutrons on the right-hand side. What's the big deal with these neutrons on the right-hand side? What's the significance of those? Why am I asking you about those three neutrons right now? Good. They can collide into more uranium atoms and cause, or nuclei, and cause, not atoms, right? We're talking about nuclei, and cause three more reactions, or up to three more reactions, which can cause 9 neutrons, which can cause up to 9 more reactions, which can cause 27 neutrons, and so on and so on and so on. What do we call that when the products, or in this case the neutrons from one reaction, cause more reactions? It's called a chain reaction. Good. So we don't get 200 mega electron volts of energy produced there. We end up getting exponentially more than 200 mega electron volts of energy because we get a whole bunch of reactions taking place as a result of this chain reaction. How do we make this one take place? These hydrogen and hydrogen don't want to fuse together because they're both positive and they repel each other. So how do we get them to fuse together? Yeah, we put a bunch of energy in there, and usually that energy wouldn't be in the form of heat. It doesn't have to be, but usually it would be in the form of heat. In the sun, this takes place all the time, right? Well, the sun's hot, so we got lots of energy to provide hydrogen to fuse together to form helium and another neutron and more energy. In fact, some of this energy, kind of like this one, the neutrons can go back and react with more uranium. Some of this energy will go back to cause more hydrogen to fuse together. Which of these reactions, reaction to reaction, this reaction versus this reaction, not like per kilogram or whatever, but which of these two reactions will produce more energy? Which one is it? Nuclear fission will produce more energy. This reaction, like one single reaction of fission, produces more energy than a single reaction of fusion. But if we have a kilogram of fuel, a kilogram of uranium, and a kilogram of hydrogen, or 50 kilograms of each, or 17.2 kilograms of each, but apples to apples, right? Equal amounts of each, then which one produces more energy? Fusion, right? Pound for pound, fusion will produce more energy than fission, but reaction to reaction, fission will produce more energy than fusion. Finally, last one that I want to ask you for now at least, one of these reactions produces highly radioactive material. Which one is it? Which one's the one that we got to worry about, 10 years down the road a little bit more? Which one is it, Isaac? Fission, right. The products of nuclear fusion are relatively harmless. We don't have to worry about that so much down the road as we do fission. Now, what is it that caused the energy to be produced there? Well, it's something that we call mass defect. We talked about that yesterday in 2 different contexts. The mass defect in the context of a nucleus was the difference in mass between the nucleus and the nucleons. What's a nucleon? What was a nucleon? Sorry? Protons and neutrons, the things that make up the nucleus. We add up the mass of all the protons, the rest mass of all the protons and the neutrons, and it gives us a certain value. That value is going to be slightly more than the mass of the nucleus itself. It's weird. The nucleus has less mass than the rest mass of the protons and neutrons combined, but it is what it is. The difference in mass there is what we call the mass defect. Now, in the context of a reaction, okay, this first definition manifests itself in the context of a reaction as the difference in mass between what we start with and what we end with. The products will always be a little bit less mass than the reactants. Okay, the difference in mass is called the mass defect. Now, the energy that's stored in the nucleus or the energy that's released in the reaction is simply going to be that mass defect times the speed of light squared. E is equal to mc squared. So if you get a question where you're looking for the binding energy in a nucleus or the binding energy produced by a certain fission or fusion reaction, then what you got to do first is get the mass defect, convert it to kilograms if it's not already in kilograms, and then you got to multiply the mass defect by c squared. How do you get the mass defect here? Well, add up the mass of all the protons and neutrons, and then subtract from that the mass of the nucleus, multiply it by c squared. How do you get it here? Get the total mass of all the product, the total mass of all the reactant, subtract them, and then multiply it by c squared. We did a couple of those questions yesterday as examples. Okay? What I want to do right now is have you work on one of those questions from your textbook. Let's go with question number 1 in your textbook on page 819. Let's have a look at this now. We've got some masses written on the board now for these different nuclei. Uranium-235 and neutron have a mass of 235 and 1. We add those up. We get a total mass of the reactants, or you could say of the parent, would be what? What is the mass there when we add those up? Who's got the number? 236 point? What is it? 0.52565. Okay, so there's our, call them the reactants if you want to use chemistry terms if you want here. Our products, we've got 93.9, we've got 138.934, and then we've got three times the mass of a neutron, 3 times 1.008665 atomic mass units. What do those add up to give me? I'm going to guess 235 point something. It's always going to be really close to what we started with, but less than what we started with. What does it end up being? 86701. Do we have more decimal places, or is that it? That's it? Okay. Now, when you're doing these problems, you got a situation like, say, the number of neutrons. You could easily forget to multiply the number of neutrons by 3, right? But the good news is if you do forget to multiply by 3, you're going to get a number that's like 234 or 233, which is too much less than what we started with. So that's an indicator that you've made a mistake in there, right, somewhere. It should be somewhere in the range of like, well, less than 1 atomic mass unit different than what we started with. Okay, let's subtract those now to get the mass defect. What do we get when we subtract those two numbers? 0. Blake, you got that? Ryan, you got that? Kira? 0.185535 atomic mass units. Agree with that? 85, thank you. Now, we got to convert that to kilograms, though, right? Good news is on a test, it would likely be given to you in kilograms already. Okay, we're just doing it with atomic mass units because, A, that's what your textbook has, and B, just in case we end up seeing something like that. We're going to say 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms equals 0.185585 atomic mass units over x kilograms. What is our mass defect in kilograms now? Kira, what is it? Okay, Okay, 10 to the minus 28 kilograms, you would expect to get a number that's really, really small, right? So there's our mass defect. That's how much mass we lose in this reaction. Now, if we want to find the energy that's released here, all we're going to do is say that number times the speed of light squared. And that's going to give us a number in joules. What do we have for that? Yeah. 10 to the negative 11 joules. Now, they actually have the answer expressed in mega electron volts. It's not really a big deal. Okay, but if we wanted to convert to electron volts, we'd say 1 eV over 1.6 times 10 to the minus 19 joules equals x eV over 2.77 times 10 to the minus 11. That would give us EV. And if you wanted to convert it to mega electron volts, you'd simply divide it by 1,000,000, right? Divide it by 10 to the 6. Right? How many people got that more or less? Got that? Okay? It's tricky because of the numbers, but it is a recipe. Okay, and if we follow the recipe, we will get it every time. There's no tricks to these questions. It's tricky in the sense that, like, easy make a mistake with typing a number in or whatever, but there's no tricks. It's always the same thing. Okay? Now, I'll be honest with you, we don't see a question like this all that often. Okay, I would say in 23 years, I've probably seen it, I don't know, a dozen times in 23 years. So maybe once, every 2 or 3 exams, we see something like this. Once every 2, 3, maybe even 4 exams. Okay, but nice thing about it, like I say, is it is a recipe. So it's like if we know the recipe, it's almost a gimme question. Unless you make a careless mistake somewhere. Here's a question that uses what's called a Venn diagram. You guys know what a Venn diagram is? Yeah, we talked about that, right? We used a Venn diagram when we looked at our electric field equations. Okay, this one was used for a non-uniform producer. These two were used for non-uniform fields. These two were used for uniform fields. And then there was the one in the middle that was used for either the uniform or the non-uniform. Here we've got a Venn diagram for fission and fusion, and we've got 4 numbers, 1, 2, 3, and 4. We know that 1 is a characteristic of just fission, 2 is just fusion, 3 is, whatever that is a characteristic of both fission and fusion, and then 4 is neither fission nor fusion, right? Okay, let's do this one together here. Match the numbers of the regions in the Venn diagram with the descriptions given below. And you can use the numbers more than once, and there's more than one correct answer. The measurable mass of the products is less than the mass of the reactants. Is that a characteristic of fission, fusion, or both, or neither? Zane, is the mass of the reaction fission less, fusion less, both, or neither? Fusion is correct, and fission is correct. So that would be both of them, right? That would mean that we'd fill in the number of 3 right there. Does that make sense, guys? How to fill that one in? The kinetic energy of the system increases in a spontaneous reaction. The kinetic energy of the system increases in a spontaneous reaction. Fission, fusion, both or neither. What are we really asking there? When we get energy released, we're going to increase the kinetic energy of the system, right? So that's going to be both, 3, 3. What's this one? 236, barium, krypton, neutrons. Is that going to be fission, fusion, neither or both? That's going to be fission. So that's going to be number, what was that, 2? Number 1. And uranium-236 goes to thorium-232, and that's going to be, what is it? What is it? Oh, it's neither. It's neither, right? That's just alpha decay, isn't it? It tricked you. You expected it to be number 2, right? Okay, how many people were thinking number 2 there just because they were being careless? Okay. You were thinking 1? Thinking fusion? Oh, because it was decaying. Yeah, I see what you mean. Yeah. Fair enough. Okay, make sense? Okay.